we continue on to the next presentation, and that is by Professor Wright. He is a faculty from IIT Kanpur in the Civil Engineering Department. He has been teaching here since 2002, and he specializes in earthquake engineering and structural engineering. He will basically present earthquake resistance of historical masonry structures, lessons of modern masonry construction.
Thank you, Mr. Patil, for the introduction. What I would like to talk in the next few minutes is the earthquake resistance of historical masonry structures. And of course, I mean, this is, we really do not know. You know, the people at that time really were designing for earthquakes, you know, as we do today. Because today, if you see, our engineering is so much diversified, and so everyone either is identified as a structural engineer. Even in structural engineers, we identify somebody as the wind engineer, as somebody as the earthquake engineer, seismologist, and so on and so forth. But when an entity is such as the oldest structures that we see, I'm sure earthquakes were there even then. The winds were there, and so is the water and other things that you can imagine. So all the natural forces were there. So the structures that had to be conceived had to resist all these forces to withstand, and of course has to satisfy the functions, has to fulfill the functions for which it has been designed. So in this context, you know, we can go back and look at the functions that or the objectives, whether these objectives were fulfilled in those structures as well. So today, when we talk about, you know, the earthquake, this is the slide that you see very often, or in context, that we need to reduce the risk of failure of the structure in event of earthquake. And that risk actually composed of three components. One is the earthquake itself, and the second is what kind of the exposure the earthquake is subjected to, and the forces are. That's the second. And third is the house, what the robust the structure itself is. So in the first slide, if you see, this is taken in 1964 Alaska earthquake, and you can see the upthrow of the ground, which is much more than the height of the hut that you see. There's a timber structure which has gone about 3 meters of upthrow there, has survived that violent shaking. Now today we create the cities like this, and then the structures that you see on the right side actually collapse. You don't notice that the one of the ground story of the structure is gone. So that's the idea, is that if you have to reduce the risk, you have to focus on the right component that made the structure withstand. And the way we do it today, we actually focus on two concepts. This is the development of earthquake engineering last 100 years. Basically, the modern earthquake engineering that we practice actually started after 1906 San Francisco earthquake, and then the people started paying more attention. And the procedures actually are coming after 1933 or so. So the idea is that either you dissipate that energy from the earthquake inside the structure. So the first two techniques are showing that we build the components such that they actually withstand the earthquake energy in itself. So one is actually going through the large movement. There may be some damage in the structure, dissipate the energy, but they should not collapse, so that no human lives are lost. The second slide is showing you put certain thing into it, such as the energy dissipation devices, that it can absorb the energy, and the structure does not get damaged as in the first case. And third one is a totally different technique in which you reduce the total energy flow from the ground to the structure itself. So such as the base isolated system. And today I'm not going to talk about that how the ancient structures or the older structures did use, you know, the combination of these three, or what portion of these three to combat the earthquake forces. But I will focus on just only one set of structures which have shown, you know, very satisfactory performance in the past earthquake. And these are the slides which I took after 2005 Kashmir earthquake. And these are very modern, I mean, like 300-400-year-old structures, sometimes 200-year-old, which have withstand the earthquake without any damage to them. And in the literature, of course, somebody refers to the Dhaji Dwari and Tak systems. In Tak system, you have only the horizontal elements, and in Dhaji Dwari, you have a very fine grid work, and the masonry actually is embedded into it. So this is from Kashmir, and then you can see all kinds of materials and variations. However, the structural system is that you have a grid work, and then the masonry components are inside it. This is the 17th story mosque, and absolutely, I'm sure the several earthquakes it has faced, and we cannot find any trace of damage in this building. However, of course, there have been few fire breakouts and some damage to the structure, but otherwise no damage to the structures. And if you see the other picture showing you that how the brick masonry is actually inlaid in the timber framework. And is it common to only India? If this thing is there, then there are earthquakes all over the globe. So we should be able to see the similar constructions around the globe. And if you travel through all the seismic threatened areas in the world and you see the older structures, you find that one thing is common, that there is all the brick is actually contained or confined in this kind of a grid work. So be it Turkey, be it the Portugal, southern France, even England, you see in 17th, 18th century buildings, we had this. In Germany, a few years ago, I was in Durham, in the city, and I was walking through the old part of the city, and I saw this building. It's a nice store, and it was preserved. And then later in the day, I was in there, the museum of the city's museum, and they had. So I was kind of very surprised to see that how this building is preserved, maintained, and of course it had all the modern amenities, electricity, Wi-Fi, whatever you can think of, air conditioning. And in that museum, they had a big room in which they had created the replica of the same building. I was very surprised to see, and explaining that how this building was actually, this particular construction type did some 400 years ago when the Durham was the coal mining city. And they were explaining that most of the structures at that time in the city were like this. But of course, now many of them are gone, replaced by the modern structures. Now, coming back to the Kashmir, you see that that I showed you the classical Dhaji Dwari construction. But even if you see the modern construction, which may be like 50, 20, 30 years old, they're also actually incorporating the effect of the elements of those. So you can see that where the timber is, they put the brick or the stone, and then the timber is, the brick is actually inside it. And of course, the top floor is usually is the traditional Dhaji Dwari construction. Now, is this the common thing of combining these two different materials? You see, one is the stone. Today, when we do is we always were very careful whenever we want to combine the materials. When we build the reinforced concrete, where is the concrete and its reinforcement, there is you'll find we're still actually studying that how these two materials should act together and what are the intricacies are. Now, even back then, in the structures you see, they were combining the stone masonry with the timbers, and there was always the grid work of the timber and then the stone going. They also had these gates in which the softer material, which is the brick, is embedded in the harder material like stones. And there are a lot of advantages having the different materials. The thermal, you can actually compensate the thermal expansion within the structure. You really don't need the the thermal expansion joint that we create in the structures all the time. We have to worry about that, do we have the proper thermal expansion? Do we have all the moisture expansion gaps? How we are handling? So I'm not saying that this has the only done for the earthquake, but of course there are many other purposes, and it's good for earthquakes as well. These are the walls, which are 500 AD. Of course, the walls have been destroyed all these years, but the towers are still standing. And this is the bottom one you see is the computer generated image that how this wall would have looked like. And you see these darker lines which are running around, or those bands which are specifically put in and to stabilize this wall against the lateral loads, which could be wind, or should be earthquake, or implosion, explosion, or whatever you can think of. Now, the way we explain is that these elements which are like a vertical and a horizontal acts as a shock absorber, because you have a softer material which can absorb energy more than the harder material, where the harder one gives you the strength, the softer one gives you more the energy absorbing capacity. And also they provide kind of a preferred slip plane. So if the structure is deforming, we actually control that how it will actually deform. So this way we control the movement of the structure during an earthquake. And then these horizontal members which continue all around, they actually contain kind of acts as as something which ties all the elements into one solid entity. So, and also they help in just the tensile forces, because as we know that most of these elements are not very strong in tension. And if you go after every earthquake, you always see that some of the old structures are standing while the modern structures have collapsed. So since the two structures are standing next to it, across that, you cannot say per se that the ground shaking was different. You see, more or less the same ground is shaking. Even the soil variations, of course, you can preclude until there is a. So you can see in the first slide the modern construction that we see very often. You have the reinforced concrete pillars or created fist, and then the masonry is put inside. And after the earthquake, you will see 90% of the times, for such structures, that the masonry has cracked, fallen out, and severe damage. However, the structure does remain, does stand in most of the cases. If you see the structure on the other side, you see which has a very uniform damage and not visible, all the elements are. And the other one here, you see that the complete collapse of the modern structure, while the older one is still standing. It may have gone some damage, but still overall performance is much better. Now, these are the pictures from the 2005 Kashmir earthquake, and here you see construction. The first one is, of course, random rubble government construction. Of course, no regard for any earthquake resistance features. See the bottom one, which is actually replicating the British style colonial construction, in which you're just using very long walls, and in one brick thick, of course, doesn't have. The other one is, of course, the old, but it's not completely using the traditional construction, because the bottom is all random rubble. There is no frame element. However, the top roof construction is the Jidwari. And typically in a building like this, as you go above the building heights, the acceleration values do increase. So the top story actually gets to see more horizontal accelerations as compared to the bottom one. Sometimes it's more than 2 times, you see. So survival of the framed masonry above definitely shows that there are a lot of inherent strength in that masonry. And the slides again compares this performance of 3 different kinds of masonry buildings and their superiority over other. So now you would ask that if the traditional wisdom existed, did anybody notice why our subsequent construction did not follow or did not use the knowledge that existed? And here is this the building when a German researchers wanted to build their medical research center in Himachal Pradesh in Nagar, they hired an American architect. An American architect coming from the New York had no experience of earthquake. In America, East Coast people don't consider that earthquake is a major problem, and their structures, they completely ignore the earthquake. However, the Western, California, of course, has more earthquake problem, and of course, people are more sensitive about the earthquake. So, in that continent also, you can see the change in the mindset about how to deal with the earthquake. So, coming here, he actually had seen that the local construction, even the British colonial structures had collapsed in 1905 Kangra earthquake. And after that, the buildings which the PWD and even the locals were constructing are of the traditional type. So, the traditional type was that you use this timber frame, go to older, the framed masonry and create that kind of a frame, and then you do that infill masonry. So, he came up with that, and he said that this is what the center should have, a building of the brick frame and infill masonry. And that building is constructed in 1932, and it still exists. This is a picture taken in 2009. So, in their journal, which they published, the Medical Society Research Center, in their issue, they actually describe that what this new building is. And this is, they say this method of construction is known here as Dhaji Diwar construction and has proved to be the best, even not only the method of construction that resists earthquake, which used to be quite frequent in this region. Most of the government buildings in Dharamsala, for instance, are built in this style and have proved to be the best. It is interesting that its essential principle, this mode of building rather resembles the steel structure of modern skyscrapers, with the difference, of course, that the wooden beams are used instead of steel girders. Thus, the wisdom of the people in its own way found the best solution, how they gave that most binding strength and rigidity with the local material available. And goes on, I'm just only quoting the portion which are applicable for the earthquake construction. So, what we see again, that not only in plane resistance, but out of plane resistance, because earthquakes is acting in all three directions, two horizontal, one vertical. So, the structure, the walls are not only subjected to the in-plane motion, but they are subjected to the out of plane. So, in plane they are very rigid, so they take forces and sometimes they get damaged, and then their out of plane forces actually push them out. So, how to have the both resistance at the same time, and that is what the grid work masonry provides you. So, it contains that, not only it actually helps you in plane, but also in out of plane directions. So, that prompted us actually to look into that what is the mechanism, how these things are happening. And this is probably my first major research project, which I wrote here in 2002. Incidentally, it was funded by MHRD that time. And what I wanted to study is to see that what is the role of the grid work in the masonry. So, in here, we wanted to replace the timber with the precast concrete elements, as the people in Kashmir say, oh, this kind of construction is not possible because the timber is not available and because of the tree felling is. So, with that, we of course did a lot of finite element simulation. In our test, we created the wall, and we could actually subject the lateral loads to measure its inherent in-plane resistance. And this is the damaged wall, which has the diagonal elements and as well as the two horizontal and vertical elements. And the bottom one is actually what we call is the butterfly or hysteretic diagram. The area underneath it says that how much energy it can dissipate. Okay, and if you see the horizontal axis, this is what we're plotting is the drift, that how much lateral displacement it can take, and it has taken up to 1.5% drift. So you can think of the building has moved about 1.5% of its height, and still there is no strength degradation. With little degradation, it can go up to about 2.5. Typically today, when we design our modern reinforced concrete frame building, we think that even the most severe earthquake, the maximum lateral drift will be not more than 2%. That's most ductile. And for masonry, we don't expect more than 0.5%. So you can see that and even after with this damage, the masonry is intact. It still can carry the vertical forces. There are more various configuration, whether the diagonal should be continuous, diagonal should be discontinuous, and we have evaluated. And then we had all these computer simulations in which we have modeled the force deformation behavior. And then the model is right. You could go and study whether what is the role of all the horizontal elements, vertical element on the strength and stiffness. These are the two parameters which we play to design the system. And finally, we actually came up with the equations which actually can help designer to choose that what kind of a pattern one wants, how many horizontal, how many vertical, what kind of the grid work, and you can design. And so this is for the in-plane actions, but we were also wanted to see that how it's out of plane. You see, in out of plane actions, we need to simulate using the shake table. So we have a small shake table on our laboratory which we built from another MHRD grant, and so we could make actually half a scale size of the wall, and which we can subject first the out of plane forces and then in plane forces, and study that is this is performance, the grid work actually does a better role. This is the test of one of the wall in which there are no internal grid elements. So you have just the boundary element and then the masonry. Typically something that we build these days. Okay. Now what you see here is that it has gone 1% drift. This is the typical diagonal shear crack that you see, and we are applying the out of plane forces which we expect in zone 5, which is the Kashmir is, and you can see that we have gone to only damage state 3, so about 1% drift, you see, and it collapsed. Now in the second one, we have just provided exactly same construction, but now it has 2 horizontal and vertical elements. Now this is a 0.5% drift. This is the maximum drift that we design, and of course we design for that, but definitely we expect that it will go more drift, more damage than this. Now this is the level 5, the ground motion. This is now the 1% drift we're doing. Now you can see that just having this vertical element, we have changed the failure pattern completely. There is no one major diagonal crack, there are only the horizontal sliding. And horizontal sliding is because in the masonry, the weak planes are the courses where the masonry is. So the bond gets broken, and then the brick actually slides and therefore dissipates the energy. Now you see that we have gone up to damage state 5, 2.2% drift. And even after that, this is able to take the full design level out of plane motion. Now, we are going up to final failure because we are now applying sinusoidal, very large force. That will never happen. That is something extremely destructive earthquake, something which is kind of, in our parlance is inconceivable. I mean, if that happens, then of course we don't expect that the structure should be surfacing. So we had gone into and to understand it better, more advanced level of modeling, where every brick we're modeling, every timber we're modeling, and saying that how the force deformation, how the force sharing is taking place. This was something where we did the static pushover, just to push the structure. Here we're looking at the dynamics, so that we can see the role of the joints. We can see the role of the frame and each brick. Of course, this is a very crude modeling because we still do not know very much the interaction of the mortar, the brick, and the at the micro level. So unless those things are understood, it's very difficult to get a very realistic. But at least here we are capturing the overall behavior. You can see here that during the process, there is a mortise tenon joint, that is what they were using the older structures, how actually it just pulls out as the ground acceleration is increasing. So we could model and see. The next slide is just showing you the out of plane behavior. So there are just only the two balls, and as the earthquake comes, they actually are now in out of plane motion, out of plane phase, and then you can see very suddenly that the masonry is falling out. And you could go, this is what the modeling of that structure, and we're subjecting it to the earthquake, and it's a large motion, and we don't understand many of these things, but we're trying to develop some of better understanding about this behavior. Now the other thing what is doing is this, the grid element that you see is binding, it's a kind of containing this masonry. So you can actually think of that you have a shoebox which represents your building, and then we wrap it up and bind it. Of course, you can see that the lateral resistance increased tremendously. So this is what is being done in this Dhajidwari construction. And one of the modern variations is something that we do the reinforced concrete frame, and then we do the masonry. If you reverse the process, that we first lay the masonry, and if we put the reinforcement and then pour the columns of the grid elements, then we get a totally different structure, whose behavior is very, very different than if we had the usual process at which the reinforced concrete member is done first, and then the masonry is laid. And this has been practiced for about at least till when the concrete construction became more popular in Latin America. And however, we do not understand that how actually does it work. Okay, people give you the technology has a lot of good things. First, is very close to the traditional practice. We know how to build masonry. And here this system is very, very fault tolerant. Even if our frame is not, the concrete elements are not actually the reinforced concrete frame as we do in the modern way, but they are very trivial members. Even if you do not make it frame, they still work. So low in intricacies in modern technology, and of course they have very inherent earthquake resistance. They perform satisfactorily in earthquake loads. Even the modern building code, such as the Euro code, does give you that how to construct this kind of walls for your buildings. And some of the advantages is like, of course, it provides you good connection between the structured walls, improves the stability of the masonry walls in outer plane as we see, improves the strength, provides the ductility so that you can dissipate more energy, and also contain the brick elements from more damage in earthquake. And many, literature has been there where especially in Mexican, they're developing the codes that how such construction can be. What we did in our lab, we wanted to compare this construction, especially when there are openings in the walls. Solid walls have a lot of lateral resistance. The moment you create the opening, their strength actually drastically reduces. Now this is the first slide. The top slide is actually a typical masonry wall in which there are two window openings, and the openings are not contained. That's how we build it. We actually raise the masonry, create the opening, and to support the masonry above, we provide these lintel bands. And so we are actually exactly doing the same test where we apply the in-plane drift of 0.5%, you create the damage, and you can see that if you remember some of the pictures after the earthquake as seen in the newspaper, the TV, you see that the damage will be all concentrated around the openings, because that is the weakest plane for resisting lateral loads due to the earthquake. And you see that those cracks are now appearing in those what we call is the masonry piers. The masonry below is almost intact. It's not participating. The sill masonry doesn't participate in the loading process, and even the spandrel masonry is very weakly, participating. The most of the thing that is happening into the masonry contained between those openings. Now we've gone up to 1.75% drift, and you can see the damage there, and the masonry is crushing, and 2.2% drift. There's a lot of damage, and then you have the collapse of the pier. If you had think of this, there's a lot of vertical load, then you have the collapse of the masonry wall. Now, if you see this diagram here, what we have done, this wall is strengthened all around the opening. So the vertical and horizontal elements fully strengthen the opening, or confine. In other words, they actually confine this masonry around the opening. So the piers are actually well confined. Now in that case, you see that we not only have the slippage or the movement in the rocking piers, but also the masonry below and the masonry above. And all of these things actually dissipate the energy. So the overall energy dissipation has improved significantly. It's just a little slight intervention, change it. And this is precisely what is being done in those traditional structures. You have a framework all around the opening, well connected, and this masonry is just a filler in them. You can see that we have gone up to 2.2% drift, and you can see the amount of damage in this is much less compared to what you have. And it's a very controlled behavior. Here also, after this, when we exhausted the lateral load capacity, we are applying 2 times of the out of forces, 2.5 times of the out of plane forces, and still the masonry is not coming out of the frame. And this is one of the plots that shows, the red one is showing the strength of the solid wall. And I just want to concentrate you on only 2 curves. The curve which is below the black dotted one, which is the curve for the second video that you saw, in which we had the horizontal and vertical elements. So it's able to reach the same strength as the solid wall. And the other thing that you notice, that it actually, of course, deforms, there is some loss in the stiffness, but it reaches the same strength as the solid wall, and can go up to much larger drift and maintaining that strength. So it's a very clear, much better behavior than even with the solid wall. And this is what in India, I think the first implementation of this thing is in the ID Gandhinagar campus, where, of course, the research and the other places where they have used this for the clay bricks, but here in this campus, they're using with the fly ash, and we at the IT did a lot of tests actually to qualify that whether they can be used for the fly ash construction as well. So here they're constructing 4-story buildings in this, and compared to the others, we have some materials. We also inspired the Earthquake Engineering Research Institute to have a site where people all over the globe can actually participate in this, in developing the masonry. So this I see that though it appears it has roots into our traditional method of constructing something which has greater earthquake resistance, just changing the solid masonry to the grid work, and of course the arrangement has a specific effect, as we detailed out that what component can give the strength, what component gives the stiffness, as we modern structural engineers actually use in designing this system. And of course we can have more rational as we develop more data on it, but this shows that what I want to say, the earthquake protection is a rather wider concept than just the reinforcing or increasing or using more stronger materials. You see, that is something that we do in a modern way that just make it stronger, but it is much difficult, at least our the traditional structures use a totally different concept to achieve the same goal. And of course, we need to see that how we can look at the older structures and derive certain laces so that we can modify our modern methods to get the same effect, or maybe better. That's all I have to say here. Thank you. Yeah.
How is the aspect ratio? Suppose the aspect ratio is 1:3, aspect ratio of the slab of the plan of the building. How does that affect the design in terms of this such level?
Well, that issue is what we call as the global issues. You see that how this whole structure is going to behave, and that is what we want to study. Through the more, the computer modeling. Once we understand how each wall behaves, then we can integrate it. Or you can test the larger structure on the sector wall. That's one way. But typically, what we have seen is the longer aspect ratio means the longer walls, and the longer walls definitely have what we call is the out of plane problems. But once you put this thing in a small, grid work, then a lot of those problems are elevated. So we can make a longer wall if you go for the grid work. That is what this study suggests.
In that case, do we have to also see the in-plane bending of the slab? Like the first slide that you showed, saying the elastic behavior.
The slabs actually in earthquake process, there are two kinds of the slabs. One, something what we call is the flexible slab. The slabs like that you have on the thatched roof, something, and the other one something like a rigid diaphragm, something like what we make for the reinforced concrete slabs. So if we have those flexible floor, then there is an interaction between the floor deformation to the wall, and what happens is as the inertia forces are acting, the floor deforms. As the floor deforms, actually it pushes the wall in out of plane directions. So that is why it's very important that the wall should have significant out of plane resistance. So that is what we call is the compatibility effect. You see, now when we have this grid work, it has inherently a lot of strength in out of plane directions. And that is why even if I include that effect of compatibility, out of plane forces, they still actually do better.
So what is the relationship of these members to the roof system, these vertical members? I mean, to tie the whole thing together.
That's right. See, in a typical system, a building system, most of the inertia forces are concentrated in the roof, because that is where the most of mass is, the roof or floors. The vertical elements are much lighter if you calculate the total load. So when the building is accelerated, the inertia forces are generated at the floor levels. Now you should have a very good connection that these forces should actually go into the walls. So that's where the connection is important. And then the forces flow down from those vertical elements from wall to the ground.
Are we tying them up in this group-wise system?
Of course.
Are we tying them up? Because
Yes.
we didn't see any slides with that, so that's why the question.
In our the test in the lab, we just separated the wall, and we are holding the wall and providing you the same stiffness which a typical diaphragm would provide at the top. So that's well calibrated support that the diaphragm will provide. Diaphragm meaning is the term that we use for the floors and roofs. Yes.
I have a question. In fact, two questions. The first is regarding the low height structures, which are generally G plus 1, 2, or 3, which you showed with the examples, the ancient buildings or medieval buildings and the modern buildings. So what will be the grid size required for these to work? Because in the modern structures also will be designed portal frames with grid, slab and columns. So it in itself is a frame structure. But in most of the cases, as per the example, they didn't work actually, practically. So what will be the ideal grid size for that? And second part is when we go for multi-story buildings, which is the normal case nowadays in the metros and second-tier cities also, for commercial residential buildings and all. So what will be the grid size for them, and like how it will work in that scenario?
So there are two issues. The traditional, of course, never had very tall buildings. They're only talking about 1 or 2 story, 3 story buildings. Now for 3-story buildings, the total vertical load that you get in the gravity load situation is small. So even the masonry walls of 1 brick thick can take. We have built about 18-story buildings, okay, in plain masonry. And so those are the multi-story buildings. Early, late 1700, 1800 actually we were doing it. Only when the steel started using, then of course we discarded and then we went for reinforcement. So you can build that, but what means is that you have very thick walls. A typical 1 brick, you can do 4 or 5 stories. And this all confined masonry in which we are not relying on the strength of this, there's a grid element for that vertical load, we can keep them very small. Okay, the load is still carried by the wall. Okay, so if you're going for something like 8-inch, 9-inch wall that we're talking about, you can go to 4 or 5 stories. Now coming to the next question, that what we should be doing for the high-rise structures. In high-rise structures, we see that there are a lot of our multi-frame structures are, multi-story structures are the reinforced concrete, but in fact, all of them actually use the masonry inside. Okay, and that masonry is, if you see, is just simple infill, and which has a potential of being knocked out during an earthquake. So what this solution is, that if you have, instead of having one solid wall, if it can be broken down into the grid, then a sub-panel, then it will have a lot more outer plane resistance, and the chances of it being knocked out during an earthquake will be very, very small. So the solution that you can do is in the multi-story is this. For the lateral loads or stability of the wall should be sub-paneled rather than a very large, what we call is unsupported length and height of the walls. So two different. Yes.
Great. Does it have to have only horizontal? I mean, which kind of a grid performs better? The horizontal, vertical kind of a one, or the diagonal kind of?
I did not spend much slide on one of because that actually breaks down the role of each of them. You see this slide. So here if you put more horizontal elements, you see, then you create a great tendency to slide. So you get actually very small stiffness, okay, and small strength. If you want more, you just put the diagonal element. So then it actually prevents the slippage of the plane, and the plane is actually now inclined. So you need more force actually for the wedge actually to slide. So you get the strength and you get the stiffness. Now, in earthquake, we just need to have a right amount of strength and right amount of stiffness. So you see there's the open ground story building. They are very, if you see that stiffness is very small because there is no masonry around it. So if we have very small earthquake, this actually this kind of construction is very good because it actually sees very less force because this stiffness is small. But when earthquake gets bigger, then it actually puts a very large amount of force demand, strength demand. And then these columns just do not have enough strength. So they actually collapse. So what we need is a right blend of strength and stiffness. Okay? And by doing this, what we have developed, that you can actually choose, engineers can choose that how much strength and stiffness you need with proper calculations. And we also developed a method in which you can design each of these vertical elements, what there should be the size, what should be their, the arrangement.
I happened to see a long time ago a video of I think Kansai Airport in Japan.
Mm-hmm.
That airport is standing on walls, huge
Mm-hmm.
iron walls, which are at the corners of the airport. So, and the whole airport actually
It's floating.
floating on the walls.
That's right.
So, but that kind of an architecture, why is that not used in operations essential of?
If I showed you that's what something we call is the base isolation. Okay, that I put this structure So this soft story, this what we call as the open ground story, is also like a base isolation system, because it has a very small stiffness. Okay, but then problem is that these columns have very small strength, and that's why they collapse. Now just imagine if I put this, remove the open ground columns and put them on a rubber pads. Okay, so rubber pad. This rubber pad is going to deform. It can deform something like 300% of its height. That's how the rubber can take. So if I allow that to happen, what happens is during the earthquake, the rubber actually deforms, and the structure actually just rides on it. Okay, so all the deformation is taking place here, and since the whole system becomes so soft, I mean I don't have those diagrams. What it does is the period, natural frequency of the system actually increases. So typical fixed base building have a natural period in the range of 0.5 to 1 second. Okay. Now once I put this on my rubber bearing, then actually I increase the period to 2 to 3 seconds. These days we are developing the bearings which can go the period up to 4 seconds. And earthquake forces are very large at a short period. So they can be like 2.5 times of the ground motion, ground acceleration, when the period is between 0.1 to 0.3 second, and then it reduces. And as you go to 3 seconds, 4 seconds, 5 seconds, this could be even less than 5% of what you have for the short period structures. So that is what we gain. So the structures just remain there. If you are in a base isolated building, you will just remain stationary, and only the ground is moving. Okay, so no acceleration transfers to the upper floor.
Some amount of base isolation included in construction here at IT.
No. There are very few base isolated building in India, because base isolation is an extremely expensive technology. We have the Bhuj hospital which collapsed.
Using soft building.
I don't have it, the traditional structures. You see, those who are people have looked at the foundations. What they used to do is to have a very coarse grade of the base material where the foundation rests. A lot of time they use the round pebbles, okay, so that they expect that the structure will roll or move. Okay, if it moves, then of course the transmission of the ground motion to the structure gets reduced. There are also people talk about the temples in the Japan or on the mud, and that mud is actually continuously kept wet because and they typically next to the lake or pond. So they have a system which keeps the thick bed of clay moist. So if it is moist, then again it's the impedance, the ability to transfer the intensity of the forces that gets reduced, the transmissibility, and that actually now reduces the ground motion that gets transmitted. So these are the some, but still, of course, there are not much concrete engineering evidence to see that it works, and is it all time wet, and what is the efficacy. And most of these temples are small structures in many ways. Yeah.
Apparently, the Taj Mahal is standing on ebony platform. Apparently, there is ebony supporting Taj Mahal. So, is that ebony performing the same purpose?
I do not know, but then they say that there are many versions. People talk about there is a well foundation, which is many stories. We do not know for sure what it is. Other people, but the one thing is that what we see is that anything the earthquake effects are always above the ground. Okay, even if you have a very poor foundation, you see the forces actually gets reduced very quickly, and so the foundation is never a matter of survival of an structure. What matters is the interaction of the soil with the structure. So as the earthquake waves are traveling, if we have a softer soil, then its wave characteristics actually changes, and those waves then get to the structure. So that's the way it is. But what kind of foundation it has, in modern ways we don't think the type of foundation actually affects the structure very much.
Now, if you factor in weight of the wall itself into these calculations, because there are many traditional methods of building in which you have very light features, like in Assam, for instance.
Ikra construction.
Bamboos, tiles, and so on, which are very all nearly weightless.
That's right.
And they behave much better than heavy masonry, which you find some parts of Himachal you find with stone infill. And in your case, how do you factor that weight of the wall?
See, the weight of the wall, the weight does two things. First the weight and the gravity loads puts the stone weight. So that's there, that's in our experiments. The second thing is when we do the outer plane motion, is the inertia of the wall. That is actually being accelerated, and that is why it actually gets pulled out. That's why you see some of my computer animation, you see the bricks flying. Probably because we haven't simulated that part. Of course the bricks don't come out like a projectile from the brick, actually fall. But that is what the force is. The force is actually the outer plane force. And that we have simulated. Since in our model we're using only half-size brick. And if you see in our model there is some lead blocks on it. You see these lead blocks? So these lead blocks are actually is additional mass, because if you have take a full prototype brick, it actually weighs 3 kg. Now this is a half-size brick, so it's a fully all dimensionally dynamic brick, and then only I can use these results. We have another study done that this half-size bricks can be used, that we predict the prototype behavior. So the weight of this is only 800 grams. But what the weight we want from simulation is 1600 grams. So to get the proper inertia forces. So each of these blocks actually representing 800 grams. So they actually add to this inertia force, but they're not adding to the strength. See? So that's why we're simulating proper outer plane forces. So it's a good question that how we do it here.
Sir, the 2005 earthquake in Kashmir, it produced lots of landslides, thousands of landslides. So the Dhaji Devar buildings, these withstood earthquakes brilliantly, but how could they perform very well in case of landslides?
Well, I mean, no, we are not talking about, there are several ground, when earthquake happens, there are a lot of effects, okay. One of the effects is, of course, the landslide. So of course, we are not looking at the effect of the landslide on the building. What we are looking at is the shaking. So there is always the shaking. So we'll be looking at the effect of the shaking on the building. So so that depends. If you have a landslide, there may be a stone falling, and if that stone actually can demolish your buildings. You see. I don't think so.
The liquefaction effects, could they have affected the building?
We still don't know. I mean, whatever, and I understand from the people who study the landslides, they do not fully understand how the landslide gets triggered. Some people say, well, if there is a weight of the structure there, then the mud is loose, and then there will be fluidity of landslide.
Soil liquefaction.
Liquefaction is another phenomenon, which is again we are not discussing. Okay? And it has nothing to do with what kind of structure you have built. Liquefaction is the property of the soil itself. Okay? So that is again is not affected by the structure that you build on it. There's a very minimal effect.
So the bit we have just done with the walls, not with the full structure.
No.
We have plans.
Well, I mean, now since you've asked it, we don't have such a large shake table that we do it, where we can do it. But in Japan, on the E-Defense, which is the largest shake table in the world, which can take a 5-story full-scale building and shake it to any strongest ground motion. They have actually tested the confined masonry for buildings, and they have also performed very well. So it's not, but it's a smaller structure they did for the